Hello. So welcome back. Welcome to the second last video on this course. And today will be a very short video. Today's session will be shorter than usual, hopefully, because we'll not do a lot of math. Instead, we'll do a lot of heuristics and architecture, which are the foundations of current uh, language models and all these chat GPTs and these LLMs and so on. So what we'll do today is I'll you go through this history of models that were sequence models. Sequence models that take in I'll do today is sequence models, and I'll start from RNNs. I know a lot of you may be already aware of it because deep learning was already a prerequisite, but we'll start from RNN, go to GRUs, and then understand what is attention in neural networks, and finally talk about self-attention and transformers. So all very simple concept. At the end of the day, some dot products with some weights. Since we have already learned making deep learning models, we have been using them for doing generative AI. This is not going to be lot difficult. This is going to be very simple instead. So first of all, will discuss languages today. Discuss encoding languages or sequences, like features in EG, stocks, etc. So what we can do is we can think of these features as x1, x2, a collection of these random variables, a random process all the way to xt. So now for the beginning, for the first most of the part of the today's session, we will be dealing with NLP, natural language processing. I'll refer you to some notes of NLP which I had taken a long time back. I don't have videos for that, but you can look at those and you can see some of the methods that can be used to find embeddings of words and things like that. So, but we'll do more, like, I think you're mature enough to understand that at the end of the day, these words that we will have, words, this is step one. And step one, what we do is, this is a brief primer of NLP. Words are embedded into, say, a d-dimensional vector space. So this is called a word embedding. And some Glove is one embedding. And there are other embeddings of Google and things like that. So this is it's not a very big deal. You can just train a model. We'll see how in a self-supervised manner, and then they will give you embedding. So these, what they do is, so you can think of these as, so say if you have a dictionary of 10,000 words, so each word wi would be represented by a one-hot vector. This will be the ith value will be 1. So this is called a one-hot encoding of the word. And when you're training this model, see here, it is a 10,000 dimensional vector space, and we really don't see similarities between words. For example, mango and papaya should be close to one another compared to mango and say chair, because they're fruits. So what is in turn done is you have this embedding layer. So you pass this wi, right? And you have these embeddings, E1, E2, all the way to E10,000, or the size of the dictionary, say. Right, so and what is actually going to happen is, when you do this, you end up getting EI. And this EI, this weight matrix, the E matrix, is trainable. So what happens in turn is, if you do a two-dimensional representation, your dog, cat should be here, and something like a fish would be, or maybe a cat, a desk would be somewhere here, and things like that. And so it will sort of categorize similar objects together, and it will separate out objects which are far away from one another. So these type of things with embeddings will do. So which xi will be in some say this is a k-dimensional space, a k-dimensional vector space, or d-dimensional vector, small d-dimensional vector space, where d is be much lesser than the dictionary size. So now each of these words are actually a real number, a vector of real numbers. Now you can, once you have a real number vector of real numbers, you can do normal AI with it, right? So let's do normal AI. So the first model that we'll do today is RNN. So all of these models could have inputs as x1, x2, xt. Outputs could be at the end, yt, or it could be like y1, y2, and this could be, these are optional. You could use the entire, for example, you could use an entire sentence and then say if the sentence was a harsh sentence or so on. So this is this, if you predict at end, this is called a classification problem, or if you classification or regression at the end, or you could have point-wise predictions. So this is really not that important, but what is important is the concept that we learned in autoregressive models, that your xt, you should have a state ht, which encodes history from x0 to t minus 1, small t minus 1. This is what is important, and therefore we have to build this recurrent connection. And how do we build that recurrent connection? We say that ht is nothing but tan h of, it's an activation function of xt plus m of ht minus 1. And if you write down the, so if you draw the diagram, this is something like this. It is rolled in time, unrolled in time. You all know this. So you will be like, we'll pass the ht minus 1, the hidden state. You'll pass xt, you'll get ht. That in turn goes to the next state. You'll pass xt plus 1. This will give you ht plus 1. And all the way till the end, which will give xt, and you may predict yt, right, from this value. And you could have different outputs from here. If you want an output, you can take the outputs. If you do not want to, do not do the back propagation. So it's like every ht is going to be taken, and then your yt is taken as a function of ht, which could again be a linear function. It could be a sigmoid of wht plus b. So things like that. It would be like this, right? So at the end, you would have the loss. You would have a loss term. So they say you predict y hat, and you will have the actual y, and you will have a loss, and this will be back propagated in time to train the model. Okay. So okay, let's try to understand the objective, the architecture once again. So the architecture takes, so it's like ht, if I, for the time being, ignore the tan h function and just take a linear function, ht minus 1 plus b. So you can clearly see that this m, u of xt minus 1 plus m of ht minus 2 plus b. And you can clearly, what is actually happening all this way here is, this is becoming a function of uxt plus, where do you get m times the memory unit of uxt minus 1 plus m squared times u of m squared times u of xt minus 2, and all the way till x0. So what is it actually doing is, the current output ht, current state depends on history. So depending on the application, you can either make it an autoregressive model. If it is an autoregressive model, this will be xt and this will become 0. For, well, it is in autoregressive models, we will try to model this as xt, and this will become 0, as we showed last time. This will be in autoregressive models, AR. Else, you can always use the HTs to take output. So this is like taking all the previous time steps and predicting the next time point, right? So let's take an example that I told you for the sentence, what type of sentence it is it is, so for example, are you going to school? So at the end, the model will classify interrogatives. The entire sentence will be read and there will be this loss at the end. So now there's this problem with this recurrent neural networks is of vanishing gradients, that long sequences are forgotten. So how do we understand that? So let's try and understand that. So long sequences are forgotten, and this is due to backpropagation in time. If you have a long sequence, RNNs really don't work, because this RNNs at the end of the day, what it does is you have to unroll it, and this backpropagation must happen through this entire blue line that I've been showing here. This entire backpropagation should happen. So if we draw this, say if you have to say the loss is being propagated from here, the dow L, dow HT, and say this is my XT, and this is my HT minus 1. So what will I want is I will try to give back the HT minus 1 dow L. I will have to return the dow L dow HT minus 1, because that's the objective of backpropagation. So what will I do is I will do this chain rule dow L dow HT minus 1 is equal to dow L dow HT into dow HT dow HT minus 1. And I know dow HT minus 1. What is this value? This value is tan H of U of XT plus M of HT minus 1 plus B. Okay, some constant. So this is a linear combination of the context vector, the linear combination of the input vector, and you're combining them together and you're taking the derivative. So this is going to be dl dht tan H dash, and you have the entire value here times M. Right? And please, yeah, this will just be the M matrix. And what you see here is this is the tan H matrix value, right? So let us try to understand what a tan H value is. So tan H of X is a tan hyperbolic function of X is defined by e to the power X minus e to the power minus X plus e to the power X plus e to the power minus X. If you're worried to how to remember tan H, it's always like you can understand how tan is actually sine by cos, right? So it's if you had just sine, you could write sine as e to the power ix minus e to the power minus ix by 2. In tan hyperbolic function, what you do is you just do not write the imaginary part. You just don't have the imaginary part in the Euler equation. You just write the power x minus e to the power minus x, which is similar to the sine hyperbolic function. So just sine half times e to the power x plus e to the power minus x is minus e to the power minus x is sine hyperbolic of x. And if you sine hyperbolic by cos hyperbolic of x is tan of hyperbolic of x. So it's just like sine of x can be written as e to the power x minus e to the power ix minus e to the power minus ix by Euler equation. If you remove the I, this becomes a sine hyperbolic function without the imaginary, without I. Okay, so let's take the derivative of this function. So tan H, that's what we want, is equal to e to the power x u by v rule, and you will get this squared, because you're going to take the derivative of the numerator and multiply the denominator. So e to the power minus x will become minus of e to the power minus x. So minus and minus will become plus, and you will get the second term as e to the power x minus e to the power minus x into e to the power x minus e to the power minus x by e to the power x plus e to the power minus x squared. So this becomes equal to 1 minus e to the power x minus e to the power minus x e to the power x plus e to the power minus x squared. So this is equal to 1 minus tan h squared. Right? So the value of the squared of this. So now there's this catch here, right? What is the catch? Where does tan h of x lie between? So tan h of x, you can write this as e to the power minus 2x by 1 plus e to the power minus 2x. So at x tends to infinity, limit x tends to infinity, tan h of x, clearly the e to the power minus 2x minus infinity becomes 0. So 1 by 1 is equal to 1. Similarly, limit x tends to minus infinity, tan h of x is equal to, if you just, it's a infinity by infinity form, so you can use L'Hopital. If you use L'Hopital's rule, so you can take the derivative of the numerator, so you'll get minus 2x times 2 by minus 2 e to the power minus 2x. And limit x tends to minus infinity. And if you do that, so these two gets cancelled, this is equal to minus 1. Right, so at minus infinity is equal to minus 1, at infinity it is equal to plus 1. So it is bounded between minus 1 and plus 1. You can take the derivative and show. And clearly at x equal to 0, tan h of 0 is equal to 1 minus 1 by 1 plus 1. This is equal to 0. This is my tan h function. So tan h dash of x is equal to 1 minus tan h squared of x, which belongs between 0 and 1. This belongs between 0 and 1. A function that is between 0 and 1, minus 1 and 1, the square is always between 0 and 1. Right? So because the square of a number less than 1 is always less than 1. Between minus 1 and 1, of course. So now what you can see is these will have this tan h function. And as I go backwards, these tan h functions would keep multiplying, right? So I would have dl dt minus I, dh t minus I will have all the product of tan h functions of u of x t minus I equal to j equal to 1 to I. So you're going to go back all the way to I, and we'll have all these values, right? Capital T minus I plus m of h of capital T minus I plus b, and it will have all the remaining terms into the rest of the gradients, into the derivatives, into say some function of h. So these terms will go to 0 because the product of these are all less than 1. If t tends to infinity, the product goes to 0. So that is why there's vanishing gradients. And model forgets longer sequences. So what is suggested as an alternative is called as a GRU, or a gated recurrent unit, where you have a single context vector, and that actually that bypasses the tan h function, which helps you taking derivatives without losing the information, right? So let us try and understand what it is like. So you can go through the notes that I've written. It's cleanly written, and you can see the model. So it's like okay. We'll start with the equations. I think we have space to do it. Yeah. So here what we will do is, to avoid vanishing gradients, have a context or history term that is not enclosed by an activation of tan h. See, the previous activation, you could have made it ReLU, but in that case, what would happen is the gradients would explode. If you have greater than 1, if these values are greater than 1, if they are greater than 1, they will explode. If they're less than 1, they'll vanish. So this is the problem with having these context vectors within activation functions for a long sequence. So if they explode, their model will not learn. So similarly, we'll have to understand this context vector that I'll have. This context vector, I'm going to keep it to be constant, but I'm only going to update parts of it. So let us see what I can do. So maybe it's good to start from the diagram. It's good to start from this diagram and show you. So in the previous diagram, what did I have? I just had this HT, this RNN had just HT and XT, and it just predicted HT plus 1, the next state. And that was being used to predict a YT if required. Now, for my preventing all this problems of vanishing gradients, what I'll do is I will have this as the network. So here, this is my context. I'll write down the equation, but it is good to see this first. And this context is not passed through an activation. Passed through activations. So this is called a gated recurrent unit. Okay. It's called a gated recurrent unit. So it's not passed through activation, and this contains the state, the current state. Right? So I will have to use xt to somehow update it somehow, right? CT minus 1, I'll have to update to get CT. So what this model tells you is it does a dummy update of CT tilde. Instead of updating the context directly using tan h function, it does a dummy update, which will be tan h of WCT minus 1, WCT minus 1, and WX XT plus BC tilde. Okay, so this is going to do a same update, but in terms of a dummy. It will store it in terms of a dummy variable, CT, right? So this is my CT tilde. This is exactly what I've written here, CT tilde, which takes in XT and CT minus 1. So now what I do is next, it's very simple. The idea next that I do is my CT, the context that I'll get next, will be a convex combination. Say I want to update using CT tilde and 1 minus update of CT. So this is minus 1. So this is going to be, see, this is a linear convex combination. Convex combination. So clearly what is happening is this gamma has to be between 0 and 1. So what you're trying to do is you're saying how important is current dummy. Dummy having info about XT. That's exactly like CT. The CT tilde has information about XT, and we're saying how important is that. And then CT is being updated, and this is the rest of the history. So now, this is the rest of the history. So now, how do you update? The question is, how do you know the update gate? So the question that I have is, how do I know the update gate? This is very simple. The idea of knowing the update gate is I will use the data itself to know update the gate, if it is important or not. So I will say my update model, say gamma u, this will be given by the sigmoid function of, it will depend on xt, of course, if I am going to remember about xt or not. Gamma u or wu plus, I will also use you can clearly see, I will also use the context that I have, the dummy context. The idea of using the dummy context is to say that have the information about the history as well. Instead of just taking CT minus 1, I'll take the context dummy itself. So what I'll do is C tilde. Do I have a C tilde? No, I don't have C tilde of C tilde T minus or T and BU. So now I have a number between 0 and 1, and this can be used to update the equation. That's the idea. This can be used to update my current context. And once I get CT, I can say YT is some function of CT. This is exactly what this gated this unit shows. If you see the equation, if you see the diagram, the previous context and XT are combined to get the dummy. And then the dummy and XT are going to get the update weight. And the update weight is used to update using the dummy and the history get the real context vector CT plus CT, not CT plus 1, but CT. CT. So that's all it is. So instead of having this in the original equation, your HT was dependent on gamma. Now I'm saying that instead this in the context vector compared to RNN, the output of the tan H is just used as a dummy. And CT has a linear context with respect to is expressed as a where CT combination of is a convex combination of one CT tilde. This is the dummy containing the nonlinearity and the previous context, previous history. Nonlinearity, XT, etc. So this is the idea. The idea, if you write down the equations again, is the central idea of a GRU is this gate. And rest is the same. This gate is the central idea where you give some weightage to updating the gate, updating the context based on the current information. That is this. And most of it, rest, is given to keep the previous history so that you have longer sequences. And here clearly, if you take the derivative with DLDC, P minus 1 will not vanish. Clearly the Vandal, there's no gradient term over here, no tan H term here directly, right? So you would be able to compute all the derivatives, at least in the context, it will have all those information. So I'll just copy this and write it down. The central idea being this. One, so when I take DL or DCT minus 1, this is just going to be 1 minus gamma U. Right, so that could contain your sigmoids and things like that, but the products wouldn't come up like that. So the idea is you would not have DL DCT minus 1 is equal to DL DCT into DL DC dc dt minus 1, right? So in this case, you would not have, you would just, this term here that I have over here, 1 minus gamma as well, and you will have this gamma tilde term as well. So this term, although this is between -1 and 1, the gradients as you go back would also depend on this CT tilde term, right? So you will have to pass them through all of these, pass this, the CT vector, which will have, is going to have this linear combination. So therefore, this, so the entire problem was due to the gradient, right? The gradient value. So now if you take the CT minus 1, this value is just going to be 1 minus gamma u of dl dct, right? And then you can just pass the gamma l minus 1 to gamma l minus 1 CT minus 1, and then you'll have all those update functions and so on, right? So this is, and this is just one of the derivatives. So dl dc minus 1. So you will have to do dct tilde, dct tilde, dct, and all of both of these terms would keep coming, and then this as well is gamma u. So you will have all this convex combination, and this won't, this term is gamma u. So dl dct tilde, this is the complete, the gradient, complete gradients. So convex combination of the gradients combination, and shown, and therefore gradients don't vanish, right? So you have all this, you can just take the chain rule and you can show that the gradients are not vanishing. And the entire thing is to have this sort of short connection from CT to CT minus 1, and you're updating it using a convex combination, thus not tan H. So next is the idea is the other form of GRU is called the LSTM, and you can study it yourself. But the idea here is two things. So here the idea is CT has the context information, but in the previous model, your HT, the hidden state, was have a difference. That is the output. Which one is the output dependent on, and which notation did I use? I'll just check once. Yeah, the output as well as the dummy, as well as the memory unit, where the same CT. Right now, I'm saying that I don't want to have the same CT. Instead, I will say that outputs will come from HT, and the memory will be CT. Will be in CT, right? The context will have the memory, and the output will be from the hidden state. So let's take the circuit. Let us try to understand. This is the number one thing that I'll do. And the second thing that I'll do is I will say, instead of having the update gate and CT tilde and 1 minus update gate, CT minus 1, what I'll do is I will make this the update gate and I will make this the forget gate. So instead of convex combination, I will use a linear combination. Okay, so this is very simple. The idea is very simple. The idea stems from this. Again, we'll have a dummy. The dummy will be used in the hidden state. The hidden state is going to give me the output. The dummies will be computed using the hidden state. And the context vector will be used to update the context vector. And finally, the context vector is going to be used to update the hidden state. So this is, let us try and understand what I mean by this. So you can see the entire notes over here, it's written, but the idea is very simple. I have the previous hidden state, ht minus 1 and input xt. So I will say that my dummy ct tilde is going to be again the same equation, tan h of w c tilde h ht minus 1 plus w c tilde x xt plus b c tilde. Now this b c tilde was being used to compute the context vector. So ct, this is going to be gamma u ct tilde and gamma f 1 minus or 1 gamma f ct minus 1. So this is my context, same context update. But it's a linear combination instead of a convex combination. This is my history. Rather, this is my current info, which I will be updating into the context vector. This is my history till t, my context history. Context by history till t minus 1. Okay, now the update vectors. How do you get update vectors? So the architecture tells me is the update vector is given by sigmoid of wu, and I'm going to club your ht minus 1 and c and your xt minus xt and du. So this is all I'm going to do. I'm going to use the hidden state and I will compute the update function, the forget gate as well. The forget gate. So this is like if when you have matrix w1 x1 plus w2 x2, we know that this is equivalent to like appending this as a single matrix and having w1 x1, right? This is the same combination, right? So this is, say, this is exactly, this is, you have a call because vector matrix operations are column space operations. So this is multiplied by this linear combination. W1 x1 is a linear combination and W2 x2 is a linear combination, right? So it is, that's why I'm just putting both of these weights into a single weight and stacking the xt's and ht's from linear algebra. So now I know. So clearly, what I was doing is I'm updating the context in terms of updating context in terms of the history relevant for output, which is my ht vector, ht minus 1 vector, updating the context in terms of the history and input xt. Okay. So that is how I update the context. Now, how do I update the history? How to update ht? So ht is given by a forget gate or an output gate times tan h of what will I use? It's the same operation, tan h of ct, the context vector ct. So how much of the ct vector that I have here of the, is it ct tilde? Yeah, ct tilde. So this is being used. It is the dummy is being used to compute the history. And my yt can be some function of ht, right? Where this gamma output gate is again a sigmoid of w output ht xt plus b output. So again, these are all t minus 1 terms. So the idea is, again, what you're trying to do is you're saying that the output is actually dependent on the current dummy, right? It is dependent on the current dummy, which has both history and current and xt information, current value information, right? Which has both history and current value information, right? So this is what LSTMs are. So you can read this in details. It's just the same architecture, but you are using the forget gate and the update gate separately. So I would ask you for more closer reading, but the idea of the LSTM is that you give more parameters to the model to actually learn and update and output the value. But what is seen in the literature is empirically, it shows that you really don't need all this different gates and things like that, right? So now what I'll do is I'll slowly get into, so what I've done is RNN, LSTMs, and GRUs are done. So we'll get into what is called attention, and then we'll finally end with what are transformers. But first we'll do this Bengio's paper, which is for translation, machine translation. So it's very interesting to see this. It's a very, very elegant architecture. So yeah, so the notes are here, but what I want you to take away is, is this. So if you want to do a sequence to sequence translation, you can see the notes later. What I'll do is I will redraw this somehow. But before that, the idea is the current output could also be dependent on the future. So the current output in translation could depend on the past as well as the future. So if you're wondering what you're doing now, we're going towards what is for sequence to sequence model or translation models. And these translation models could be used everywhere. So if you have a question, a chunk of summary in a chat GPT, the output would also depend on, if you have to give an output in terms of read it, summarize it, it will depend on the past and the present and the future. The tth point would also depend on everything in the future and so on. So if you have a sentence like this, that I am going to school. So here you can see I depends on the first time. School is at the end, but Vidyalaya, when I'm transferring it to Hindi, is actually dependent on the end point. So you will see that the translations, you often require a bidirectional LSTM. So what a bidirectional LSTM is, so what it actually requires is your X1, you feed it, so your X1, X2, you feed it to two LSTMs. You say you have H1 forward or H2 forward and H2 backwards. You have two parts of this model, H1 forward and H1 backwards. So what happens is all these, this H2 is actually, this is the LSTM that goes back in time. And this is the LSTM that goes front in time, right? And these two are used as a common feature for prediction. H1 is the concatenation of H1 forward and H1 backward, right? You use both of them together. So actually what is happening, you have an LSTM that takes in HT plus 1, XT, and we have another LSTM. You want to draw them separately, or any recurrent unit, which takes in HT plus 1 and outputs HT. It is going back in time. This is going to predict T from T plus 1 this history of this is, the history is defined as t plus 1 to capital T, the end. And for this, the history is defined for 0 to T. Right? So this is depending on whether you're wanting the information from the future or the past. This is going to be defined in such a way. So now, what sequence to sequence models do is that, so you say you have these, not going to put on the diagrams, H1, H1 forward, and I will get the H1 vector. Similarly, I will get the H2 vector, H3 vector, H4 vector, H5. You can see the full diagram here. This is the fair diagram. And look at it. But the idea is that my x's, x1 is fed to both these LSTMs, x2 is fed to both these LSTMs, x3 is fed to both these LSTMs, x4 is fed to both these LSTMs, and x5 is also fed to both these LSTMs. I am going to school. Right. So now what it says that, okay, very good. I will have another decoder because the output could have a different sequence length as well, which will have S0. Now S0, the out, this is my encoder decoder model. This is an encoder. And these HIs will be used in decoders, right? So these HIs will be used in a decoder. And how will I use this is the question. I could just have used this HI, but that is not a good idea. I will need all these HIs and I will need to combine all of them somehow. And let us see how will we combine this, and we will get something called as, say, CT or C0 here. And then this will give me S1, and then similarly I'll get C1. So I'll show you how I get this. This is the entire thing of attention. This is where attention comes in. Attention-based mixing. Bengio gave this in 2014. This is cross attention, because we are doing a cross attention across the input and the output. So yeah. So now we will have C1, and then you will have S2, C2, and dot dot dot. So this will become my Vidyalay Ja Raha. So this is what it will end up being. So here you can see here this end word that I have, H5 is important, or rather here. It is not worry about C0 because which is going to be similar to C1. So if I have all of these words, so in this case, I will put this red line over there. This is the most important word for translation. Important. Because it says school, I'm going to school, and this is the Vidyalaya word. So this is actually the most important word. So what attention says that, attention says, say my output is, corresponding output is Y1, right? So what I'll do is, so where did I put this? So you could have Y1s anywhere, but if my attention says that C1 or C2 is going to be the summation of, what is it going to be summation of? It will depend on all the context or the encoded values. So this will depend on all HIs, right? And it will depend on alpha 2i, I equal to 1 to say capital T, right? So this is if alpha 2i is tending to 0, that word is not important. If this is high, this is a relevant word for translation. So what it means is it's like a human attention only. Human attention, what it does is you have this remarkable phenomena where you have all this noise coming in and everything around your surroundings and things like that, but you're only attending to what I'm saying currently, hopefully, which means that you're able to suppress information everywhere else, but only have information where it is relevant. For example, here the school word is relevant for my current word Vidyalaya. Okay, so this is what the context vectors are in attention written as. So it's written as alpha I j's, j equal to 1 to t. Now you will ask me, how do I get alpha i's? So now that is a story next to consider. So we have seen the yi's will depend on this. So did we write zi's? Okay, let us just put zi's if to have no context information, z1, z2. Okay. Right. So now you will ask me, how do I get alpha i's? So say the alpha ij, j equal to 1 to t is equal to 1. Say these are probabilities. These are probabilities. That is most likely matching word is given highest importance. Right? So this is a probability. So how will we make this a probability, and what is the procedure that I'll be using? That is a very, very good question to ask. So alpha ij is some similarity. Do you agree? So they will have this matrix where I have x1, x2, x3, xt1, and you will have y1, y2, dot, 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 yt2. Right? This alpha ij that I have is the similarity between. So this is my, what is the relevance? Rather, I should have the y's on the y-axis because y's are the first index. Yt2. So here, so this is say the alpha ij. What is the importance of input word xi for predicting, or the output word yi. I shouldn't write this, sorry. What is the importance of the input word xj for predicting the word yi? Right, so that's what we are doing. So this is some similarity matrix. This is proportional to some similarity between. So xj has to be some hj, right? Some hj, and this is the encoding for aj, right? And you could have the other one as, say you are predicting zji. This could be j, you have the access to si minus 1 only. And that si minus 1 could have the information relevant to predict the current yi, because you don't have zi access to you directly, because zi can only be accessed after you have all the alphas. So you use the context and you use si minus 1. Right? So you use the context because zi depends on alpha i's. On alpha i's. So, or alpha ij's. So we need to find similarity with the previous context vector. So now this has to be equal to 1. The summation over all the j's should be equal to 1. So we will make a softmax function. So where this alpha ij is equal to e to the power exponent of some c theta model Si minus 1 hj by summation of exponent of c theta of si minus 1 hj j equal to 1 to t. So this is also called the softmax of c theta si minus 1 xj over all j's. That is inputs. To softmax over all the inputs. So the idea is very simple. It returns to me a probability distribution with maximum importance to the relevant word. And this C theta could be a shallow neural network. And it will say, it will learn this, that the similarity between Vidyalaya and school is high. So it's very, very simple idea. You have an encoder and you have a decoder. And the encoder gives you all these HIs, and this decoder takes in all these HIs and predicts the next token. Right? So this is called cross attention because the attention is working. This is called the Benju attention. It's called cross attention because alpha is in the space of Ry cross Rx. Right? So this is number of, so all these terms are there. What is the importance of the xi input for the y's output? That's the idea. So now we will, what I'll do is, so we have understood LSTMs, we have understood GRUs, we have understood attention and so on, which is as a similarity, which is important between two terms. So now what we will do is we will convert this attention to the recent attention paper. The attention is all you need paper by Vaswani et al. This paper says attention is all you need. It's a pun on the word attention. This is the title of the paper. And it will say that it is, I'm just going to talk about the encoder block. And then at the end, I'll show you how the decoder block is implemented, encoder block. Right? So the encoder block is what we'll be talking about. And whatever we did with these, so which means that this is going to be only this block. And this block, I will say, in the Seq-to-Seq model, this paper claims in the Seq-to-Seq model, we don't need bidirectional LSTMs to encode information. So instead, what we can do is we can just use word similarity or attention amongst oneself. So let's try to understand again. This encoder block again will give me an output. This encoder block will give me an output of RD plus T, and it will also output RD plus T. Where each is d-dimensional latent and T is the number of time points. Right. So we saw that in the Benjo paper, it was cross attention, but now we will say that we will only do self attention, which means that what I'm trying to do is I want to have this block. This block diagram is often helpful, self attention, which will take my x1, x2, and xt, all my input. It will combine all, mix them, and give me my encoded value. Right, and often this for generality, we can write this as y's as well. So if I will not write this as y's for maybe for your understanding, do I have y's? So let us write this as h instead. as it is the encoded block. It's the same length because it is the encoded block, right? So what I'll do is I'll convert this into access to H, the hidden layer. So how will I convert it? I will say that all this while I was computing this matrix alpha, where alpha 1, 1, alpha 1, 2, and alpha ij, similarity of yi with xj was being computed. Instead, I will say that since I only have x's, why not compare similarity, self-attention. In self-attention, it is cross-attention. In self-attention, let us compare similarity with word xi and xj. Between words, not with words, between words xi and xj. So, right, you can simply do that similarity measures by say wi j as just xi transpose xj, where xi comma xj are the embedding vectors of word I and j. Okay, this simply we can do this, and then we can say that my hi output is just the summation of wij xi or xj. Right? So which is nothing but equal to saying summation over j equal to 1 to t w, or this is nothing but xi transpose xj. That's all there is to self-attention. So you're saying that my current output, whatever my output is going to be, H2, is going to be through this similarity that I'll be computing between these words. So H2 that I have over here, right? The H2 will depend on what is the similarity of X2 with the rest of the sentence. Isn't it? This is what I'll get H2 to be. See, the xi that I have is corresponding to the xi, and I will see what is the similarity of x2 with respect to everyone else. So this term here, for example, will be x1 transpose x1. This term will be x1 transpose x2. This term will be x1 transpose x3, and so on. Right? Great. So this matrix, so my H can be directly written as x transpose, which is, you can clearly see if it's a t dimensional vector. So this is my what was the dimension that I was taking? Say it was t dimensional, and each of them were d dimensional. This is d cross t, or t cross d. So this is also equal to t cross d. That's all we want, because we want the output. So this is something like this: h1, h2, dot, ht. This is equal to the similarity matrix w d, or similarity t cross t, and you have the x matrix x1, x2, x3, xt. Right? This is how I combine w's with the different x's. So it's like w11, w12, w1t. So it'll take the linear combination of the rows and give me the output of h1. So this is all there is to self-attention without any learnable parameters. Right? So without any learnable parameters, this is what is self-attention. But you can see there's a similarity here. So what is the output that I want? I want the output. So there is this is the So there are a few drawbacks. This is self-attention. These similarities are already known, and there are no learnable weights. If we will have to make it learnable, the patchwork that I have to do is make the similarities learnable. And the input and the output, the other is the input and output are same shape. If we want different shapes, we will have to have a decoder block, decoder transformer, and we will see that. We will see how to do that. Okay, so first let us make the weights learnable. How will we make the weights learnable? But before that, let us try and understand what this can be understood. This X transpose, again, this should be Y H1, H2, Hn. The first thing that I want you to understand, the key, query, and value interpretation. Okay, so now again, I will redraw this block diagram. I have X1, X2, Xn, H1, H2, Hn, right? So if I have this is the block diagram, and I want the value for H2, right? So what should be my question for? My question, the query vector should be X2, right? Because you remember my H2 is written as the summation of, this is non-learnable, X2 transpose Xj times Xj, right? My query vector is for X2. So I'm trying to say how similar is X2 with each of these vectors. So I have these keys now that I'll compare with keys, and I will do a dot product. Keys will be X1, X2, dot, 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 Xt, and I will see which key matches the query the best, right? This is exactly like a DBMS thing. You put the query and try to see which is the key that matches the query. So and you see which token matches the query token. And those will have high similarities. Those will have high weight. And then you will use them, and your X2 value, the value will be taken, and this similarity W2J, and then the value of Xj will be taken, and this will output Hj or H2. Right? This is the Q query value pair idea. So you have a query for a corresponding term, and you try to see what is the key, and then you try to match the value of the corresponding inputs or get the outputs. So now this is the query key value output. So this is the H, this is X. So okay, so now how do I make them trainable? So I can say that this is my query, this is my key, right? This is my key. I'm asking for a particular answer, so this is my query, and the key is, which of the following should be the query? You tell me. Should the query be each of these Xj's, or the query should be? So the idea is it could call the either as query, but the query should match the key. Wherever the query is matching the key, only those keys will be returned, right? So the keys, what happens at DBMS is you make a query, and the keys that matches the query is returned. So That's exactly what is happening. So for a particular input, you have a query and you have the rest of the keys. So fine. So am I doing this wrong? Am I mentioning this incorrectly? So I think this is called the key. And this is called the query. Yeah, because we are making more queries than keys, right? So key is the corresponding output you want, and you want to make different queries to see which token matches the key token. Those will have high weight, right? So the key is fixed, right? So you have a particular key and you try to see which of the queries that you have, the KT queries that you have matches the key. That's the idea, right? So the value is the QK transpose times V. This is the idea. So this is my value, this is my key, and this is my query. Because we wrote this before as well, that this is nothing but XX transpose times. So we said before, we showed before, H is equal to X transpose times X. And I'll say that I will make this the query. This is my key. And this is the value, right? So I'll make each of these X's in turn learnable. So what will I do is I'll say Q is equal to WQ times X plus, or just QX times BQ. K is equal to KX plus BK. V is equal to Vx plus V. And you can learn these values so that you don't have fixed parameters. So this becomes the H becomes equal to QK transpose times V. And to decrease exploding gradient problem, and again, this has to have a softmax. Remember, because as you will remember, since this is fine, but the summation of Wij, this is proportional, okay, should be equal to 1. So therefore, Wij is exponent of Wij by summation of exponent of Wij. So you go sum over the rows. So this is softmax. So H is given by, and this is softmax of QK transpose over rows, right? So query vector again is like T cross D. This is D cross T, and this is into V. So this is going to be each row is a T valued distribution. Okay, so now to have numerical stability, the paper showed numerical stability, QK transpose, so that softmaxes could be computed. You divided it by the dimension of the data. So you have numerical stability, you divided it with the dimension of the data. That's the paper's hack. So I think my tab screen is not visible, is it? Yeah. And therefore, the self-attention block is often written as, this is my self-attention block. If you write this as this, you can think of this as Q, the query key and value pairs, and this is computed from X itself, and you have H's, the hidden value, or this is self-attention block, and you have the key value, the triplet of query key value, and you have the hidden state. Right? We're almost to the end, but now how do we use this architecture? The architecture says that for an end-to-end mapping, what you will do is you will have these multiple attention blocks, self-attention 1, self-attention 2, and you will pass X to all of them. Say 3 to 5 blocks you will have. And then you will merge them using an MLP. And then output H again. Again, H will have the same dimension as the input. So this one block. This will merge and give you the output as one block. This is called a transformer block. Block, compress. This is multi-head attention. Multi-head. So you have multiple attention head. Each of them could pay attention to different features. Maybe long distances could be some could pay attention to summaries. Some could pay attention to grammar and things like that. Some people pay attention to characters and things like that. So you have multiple attention blocks and you have MLPs. And use multiple of them, say transformers, 6 to 7 of them to get a GPT or things like that. So you could have multiple repeating transformer blocks, which transforms from one sequence to the other, but each of them these are all at the end of the encoder blocks, and you end up training an entire transformer. So a transformer at the end of the day will take X, it could have multiple T1. This is how the paper shows it, and it will give you an output of the same dimension. It could be used as an encoder model where you could learn embeddings. Embeddings, for example, if you have this entire sentence, you could remove a word here and use all the rest of the X's to predict this word. Predict. You can mask them and use for prediction. You could use it for autoregression as well. But remember, this idea, the Q query value pair, a transpose by root D is a bag of words model. That is that x1, x2, xt, x2 and xt, if you replace, the columns are going to change. Columns in QK transpose will change. But value will change accordingly to outputs won't be different. So this is the sinusoidal embedding thing. Sinusoidal embedding or position embeddings. So therefore, order is not present in self-attention. Right? Order is not present in self-attention. So therefore, what you end up doing is you append t equal to 0, t equal to 1, and all the way to t equal to t minus 1. And you append it. We have seen sinusoidal embeddings. You could do the same sinusoidal embeddings. By cos of t by t to the power I by t. And sine of t by t to the power I by t. And we have seen sinusoidal embeddings for refer to diffusion models. Model session 5 for details of position embeddings. This is all about transformer architectures. So now I'll end today's session to see how we can make this transformer architecture an autoregressive model. So the autoregressive model is saying that I'll be able to predict x1, x2. I'll be predicting x3 here, but x3 will only have access to x1 and x2, right? And not the future. So if you have to mask the future, if we have to mask the future, how would you do it? Right? So we have to do something like this. So my H W2 should be only dependent on W11 or W21 X1. Similarly, H3 should be dependent on W22 or W21 X1, W31 X1, W32 X2. Right? So you can clearly see I would want zeros to come for the rest of the values. And to zeros to come for the rest of the values, you can clearly do this QK transpose by D, and you can add this matrix of minus infinities and zeros over here. If you have minus infinities and if you take softmax, the probabilities, the weight vectors will all become 0. So this is my QK. This is making autoregressive, making the transformer autoregressive or masking the future. Okay. This is how the model decoder models are trained, and then you will have so W21, W31, W32, and dot dot dot. Only the past is going to be used. Right? This is the mask. This is the mask vector, mask model. Right? So now, when you have a decoder block, all the transformer is going to do is going to take X1, mask everything in the future, predict X2, put it back to here, predict X3, and so on. Right? So you can do it like this. You can just roll the transformer over and draw another transformer. Right, X1, X2, predict X3, and then right. And this will all be done together because we'll be able to use the mask. The use of the mask will take care that the future is not being used. So this is my decoder block. So decoder, you take an X1, pass the X2 back to the model, X1, X2 the model, X3 will be predicted, and so on. Right? If it is an autoregressive model, X series of X's are predicted. If it is not an autoregressive model, this is a language model. This is how it will be predicting. If it is, you have predicted different Y's, you could just take X1 and X2 and predict X2, Y2 and things like that. So depending on the architecture, you can just add the softmax over the infinite softmax, and then that will be making your transformer block. So I hope that is clear. We have been able to make different sizes of transformers, and we have shown how we will make them autoregressive. And with that, I will come to the end of language and sequence-to-sequence models and also autoregressive models. I hope you'll be able to now understand transformers and GPTs better as a language model which predicts the next token and things like that. And we have covered mostly all of the models that are there in language models. In the last class, the next time, what we will do is we will end with another generative AI model, which is called the recognition parameterized model. And the recognition parameterized model is going to compute likelihoods, but it will not keep giving you new data points. So that's the plan for the last session. And we have completed 6 modules today. And if you have any questions, please feel free to ask. And we'll see you in the next class. Stop recording.